So moving on, then we need step 3. So step 2 was separate the variables, figure out which sign goes on which direction, and then 3 is solve the eigenproblem. So I've used this word eigenproblem. I mentioned that we want to have a repeating solution, right? We want in the homogeneous direction to have a solution that repeats itself. Why is that? It's because we're going to actually find a set of solutions that when you add them together, give you the full solution. That set of solutions, maybe you remember from, I don't remember which calc it is, but you go through this eigenvalue, eigenproblem process. The set of solutions comes from solving where the sine and cosine functions hit their root in a repeated way. So the eigenproblem is this one because it gives us the repeating solutions. So we're going to solve this one first, right? This is the homogeneous direction. Okay, so solving the eigenproblem, again, like all this is that pattern matching. So we went to the table, and we get back our solution for t of x. So t of x is equal to c1 sine of lambda x plus c2 cosine of lambda x. Right, that just comes from maple, table, whatever you have. Note again that we have 2 unknown constants, and our job is now to figure out how to enforce boundary conditions on this. So we've got this eigenproblem. Where are we going to get the boundary conditions for this? I probably should have copied them over, but we have, for our problem in x, we want to first look at the boundary conditions that correspond to that direction x, right? So our boundary conditions were what? Let me write them out here. So it was t at x equals 0, and then we had dt, sorry, the partial t with respect to x at x equals w is equal to 0. Right? These are our 2 boundary conditions that we're trying to enforce. So okay, so we need to enforce these boundary conditions, but it's important to note that t at x equals 0 is the full temperature, right? It's t as a function of x and y. We now have a function that we're only dealing with t of x. So when it comes time to enforce the boundary conditions, we need to actually make the full substitution, evaluate the boundary condition, and see how it might change. In this example, it doesn't really change that much, but let's go through it just so you can see the steps here. So we're going to make the substitution t at x equals 0, and that's going to be tx times ty evaluated at x equals 0 is equal to 0, right? This is just making that original substitution. So we have to look at this and use a little bit of a process or some thought to figure out how do I need to actually change my boundary condition to get this to be enforced. So what I mean is, if let's say t as a function of y is 0, that would satisfy this boundary condition, right? No matter what tx is. But because this is the homogeneous direction, that actually ends up not being an interesting solution, right? tx is the condition that has to be 0. So in this function, we let ty be whatever it is. This boundary condition is just telling us that because this is a homogeneous direction, this tx has to be 0. Okay, so that's a little confusing. Okay, so but tx at x equals 0 is equal to 0. But the point is, you have to think through that you have 2 independent functions, and which of the boundary conditions, or how does the boundary condition apply to each of those independent functions, and how do you get a meaningful result out of that? Okay, so that's boundary condition 1. Now we can actually enforce that boundary condition because we have it in terms of our function here. So if we do that, what? Let's see. Actually, I'm sorry. Let's look at the other one first. So this is boundary condition. Let's call this 1. Let's look at the other boundary condition, and then we'll enforce them. So boundary condition 2 is dt dx partial t with respect to x at x equals w equals 0. So substitute in. Now we're going to say partial of tx times ty with respect to x, partial with respect to x at x equals w equals 0. So we've just made the substitution. So I guess what can we do again here? We can say this is a partial derivative with respect to x, so it doesn't affect ty at all. So we can pull ty out front. And we're left with ty times dtx dx at x equals w equals 0. So there's like same as the one above, and it's kind of like a trivial, or it's like a weird step to force ourselves to do, but for these simple boundary conditions, it feels unimportant, but as you get more complex boundary conditions, it might become important. So what ways can we satisfy this relationship? We could either say ty is 0 everywhere, or we could say the partial of the tx with respect to x is 0 everywhere. So again, like saying ty is 0 everywhere is not helpful. So that goes away, and we're left with just the boundary condition here. We're again trying to figure out how these boundary conditions apply. So okay, now it's just dtx dx evaluated at x equals w is equal to 0. Okay. So we've successfully translated our boundary conditions into the x problem. Now we can actually enforce them, right?
Do you have an example of when it might not be trivial?
That's a good question. So off the top of my head, probably not a great one. What would be? So yeah, I mean, I'd have to think about that a little bit more. For this class, what we end up doing is almost always, we go through this step this time just to show you that you have to think about it. But when it comes to the homework and stuff, you say, okay, I'm going to make this assumption, or you state it, and you just move on, right? That's kind of it. Yeah. I'll try to think about that and let you know. But okay, any other questions? Yeah.
So I'm just confused when I go back to the TX, TY equation. Both boundary conditions.
So, sorry, can you say that again?
I'm confused why you go back and say TX times TY. Like, why are you evaluating at that equation versus TX?
Yeah, right. Okay, so if we look at our problem, this problem, these boundary conditions apply to the temperature function Tx of y, right? The full function. So the entire function t x and y has to equal 0 at x equals 0, right? So when it comes time to enforce the boundary condition, we have to make sure that we're doing that for the full function. So like if we look at the substitution here, well, all this is saying is, yeah, when I enforce that boundary condition, I'm going to make sure that I enforce it knowing that really this applies to the entire, entire function. But because I don't want ty to be trivial, I'm just going to enforce it on x. Or basically, I can just get away with enforcing it on x and have it be valid for the problem. Right? So it's a way of like throwing out part of the problem that's not relevant for the boundary condition and then being able to move on.
Isn't it just restating like what we already assumed, that t is just the product of tx and ty?
It is, yeah, in a way, yeah.
Is the actual temperature product of TX and TY?
I mean, our model says it is.
So TX is an actual temperature. Like, it's not.
Yeah, like, okay, so let me just sketch something here.
We're going to have to do this calculus.
So let's say I have some temperature. It's going to be some normalized temperature, whatever, and I have some normalized position. So this would be like x from 0 to 1 and y from 0 to 1. What this is actually saying is, for this problem, I have some function. Maybe it looks like this, and this is tx. And this function has special properties. For one, its temperature is 0 at x equals 0. So that's homogeneous. 2, despite my drawing, dt dx at x equals w is 0. So this is a homogeneous boundary condition temperature profile. The other thing is, okay, now we have another temperature profile. Maybe it's something like this, right? Now this is Ty. This here was T. Yeah, I already got it. Tx. We're just saying that I can get the actual temperature function by multiplying these two things together at any combined position x and y. So, yeah, pick a position x and y. You take the product of those two functions at their respective coordinates, and that's your temperature profile. And this only works if it's homogeneous in x.
So maybe you already said this, but to make it homogeneous in x, t has to be like dimensionless or normalized. Otherwise, right, it doesn't make sense.
No, it does. It doesn't have to be normalized or dimensionless. It just has to. I guess the idea is that if you had two functions where the boundary conditions weren't homogeneous, like let's say we had our tx function and it was here. Now, when I'm multiplying this function by this function at x equals 0, you're like scaling the temperature. You're like offsetting the temperature from what it would otherwise be, where this sort of this normalized thing.
Yeah, so like in our problem, we're saying one of the boundary conditions is 0 and one's th, but it really just matters that it's a delta, right?
In the example problem?
Yeah. Because otherwise it seems like unphysical to say that your boundary's at 0 temperature.
Yeah, so the whole reason why this is...
So you either have to subtract or divide, right, to get to 0? Or
That's, yes, we can, and you're spoiling my last slide.
sorry.
No, but that's a really good point. I mean, so you can have like tricks or substitutions that you can get to simplify the problem down to be homogeneous boundary conditions. It's not like it only applies in cryogenic conditions or something like that, right? Yeah. Okay. So let's see, what are we doing? So we have our two boundary conditions now. They're expressed in terms of the just the x function. So we need to solve the eigenproblem. So let's see, I might run out of room. Let me just erase some of this stuff. All right.